What if you could regrow a lost arm? Imagine the scene. A sudden, violent accident on a busy city street. In the aftermath, a limb is gone. The trauma, the loss, the long road of recovery. But what if that road led not to a prosthetic, but to a new beginning? Imagine weeks later. Where the wound once was, something new is happening. A small bud of tissue forms. Over months it extends. It differentiates. It grows. Bone, muscle, nerves, skin. It looks and works just like the one you lost. Sounds like science fiction, not magic. In nature, this is a daily reality for many creatures. That idea forces us to confront the limits of our biology and ask how this could ever work in us. First, we explore the biological wizards of our planet. Salamander, zebrafish, lizard, then turn the mirror on ourselves. The process of a lizard regrowing its tail can be broken down into clear, step-by-step biological events. It all starts with the wound. Immediately, a rapid but special kind of healing begins, not the scar-first response we see in humans. Epidermal cells migrate to cover the stump and form a wound epidermis, a signaling center, not a mere bandage. With the surface sealed, the blastema forms beneath, a mound of undifferentiated cells, biological clay ready to be shaped. Cells from muscle, cartilage, connective tissue, and skin de-differentiate, forgetting old jobs, returning toward a stem-like state. The blastema grows fast, fueled by rich blood supply, and guided by chemical signals from the wound epidermis. Imagine a 3D printer, except it builds with living cells layer by layer. As the tail elongates, patterning begins. Cells redifferentiate into muscle, cartilage, skin, and reconnecting nerves and vessels. The body remembers the original design and rebuilds it with remarkable fidelity. In the end, a fully functional, sometimes slightly different, new tail emerges. The blastema is the true hero of the regeneration story. It briefly returns tissue to an embryonic-like state, reactivating powerful developmental programs. This is where salamanders diverge from mammals. Blastema versus scar. Think of it as a construction crew assembled on-site from recycled parts of the old building. Cells deconstruct, then reform, locally sourced, abundant, and perfectly host-matched. The apical ectodermal cap manages growth. Incoming nerves provide essential go-ahead signals. Cut the nerves, and regeneration withers. The blastema self-organizes. Cells decode positional cues, becoming muscle at the base, skin at the surface, cartilage in the core. It sculpts, then disbands, leaving a fully formed limb where none existed. A living blueprint for rebuilding, hidden in plain sight. Humans, for all our complexity, are fundamentally different in how we respond to injury. When we lose a limb, survival comes first. Stop bleeding, prevent infection, then inflammation surges. Scar tissue forms, a quick patch of dense, cross-linked collagen laid down by fibroblasts. Strong, sealing, but a dead end. It blocks cell migration and communication, so the blastema never forms, and complex rebuilding stalls. Our healing is a fortress wall, not a construction site. Salamanders show a modulated immune response. Humans unleash aggressive inflammation that drives scarring. Our cells are locked into mature roles, with limited plasticity. We have stem cells, but too few, too restricted, for whole limbs. Nerves differ too. Salamander nerves drive regrowth. Our intricate networks are hard to recreate after severe damage. We've traded regenerative potential for a powerful immune system and highly specialized cells, advantages with a hidden cost. So, if our biology is stacked against regeneration, can science change the rules? One major path. Stem cells, the body's master cells that can become many types. Scientists harvest, expand, and guide them, aiming to seed injuries with cells plus cues to build new tissue. Essentially, an engineered blastema where none forms naturally. Early wins, patches of heart muscle, cartilage for joints, and organoids grown in dishes. Tissue engineering adds 3D printed biodegradable scaffolds, frames seeded with cells and growth factors, a trellis for living growth. Another avenue, gene therapy, to reactivate developmental programs at the wound, precisely and temporarily. Tools like CRISPR could flip genetic switches toward regeneration if we build safety circuits, timers, and drug-dependent off switches to prevent runaway growth. It's early, mostly animal models, but precise editing opens a thrilling, challenging frontier in regenerative medicine. Beyond genes and stem cells lies bioelectricity, the body's quiet, instructive currents. Cells maintain voltages that form gradients, patterns that may guide how tissues organize. In regenerative animals, amputation triggers a distinct bioelectric signature at the wound, like instructions to rebuild. Michael Levin's lab altered a frog stump's electrical state with a drug cocktail, and triggered regrowth of a functional leg, toes, and toenails included. No gene edits, no added stem cells. They simply changed the electrical conversation. The genetic instructions may still be there in adults. The missing piece could be the bioelectric trigger. Enter electroceuticals, smart bandages and wearable devices that modulate wound bioelectric states to prevent scarring and encourage blastema-like growth. The leap from frogs to humans is huge, but this paradigm shift opens a safer, subtler way to orchestrate growth, guiding rather than forcing biology. The potential benefits are staggering. Trauma care transformed, millions with limb loss offered living restoration, from accidents and battlefields to diabetes and disease, regrowing a functional limb would surpass prosthetics. Quality of life, mental health, and personal independence immeasurably improved. The same principles could help hearts, pancreases, and other organs, repairing damage we now only manage. But risks loom. Regeneration uses growth's fire, the same that fuels cancer. Control and shutoff are paramount. Who gets access? Will cost create a divide? We must set boundaries around enhancement and ensure equity. Science must move with ethics, public dialogue, policy guardrails, and long-term safety studies. The science is racing ahead, and our ethics must keep pace, so healing narrows gaps rather than widening them. The dream motivates, but timelines matter. Progress will come as small, steady wins, not one dramatic breakthrough. In 5 to 20 years, better wound care that reduces scarring, more effective lab-grown skin and cartilage therapies. Prosthetics and brain-machine interfaces will advance. More lifelike, more sensation, more intuitive control. These devices will bridge toward biology and teach us how to interface a future regrown limb to the nervous system. Whole limb regrowth is a mid to late century challenge, likely a combo of scaffolds, stem cells, targeted genes, and bioelectric guidance. Be honest, this is a marathon. Steady, responsible progress builds trust and real futures. Better grafts, joint regeneration, then digits, then hands. We began with a shocking question. But this isn't fantasy. Regeneration is an ancient program alive in other creatures. The path isn't single. It's convergence. Genetics, tissue engineering, developmental biology, and ethics together. We must speak our cells' languages, chemical, genetic, and electrical, to persuade the body to build, not scar. Each success, and each failure, teaches the dialogue needed to heal what was once irreparable. The power to rewrite limits carries responsibility, control cancer risk, ensure fair access, and build wise guardrails. So we end where we began, a regrown arm not as fantasy, but a destination on the horizon. Let's make that future both healing and human.